Well, let's get going. My name is Dave Hammond. That's Luke Donfor. Luke runs the teaching labs, and I do lecture demonstrations and other various things, and we team up for events like this. So today we're going to cover a variety of items. We're going to talk about initially some properties of materials, some different aspects there, and then we're going to do some air pressure demos, and then some electricity and magnetism. So first we're going to talk about some properties of different types of materials, but I'm going to need a volunteer for the first part of this. Anybody? Okay, you're 8th graders, right? See, if this was 6th grade, if this was 6th grade, every hand would be up. Yes, there you go. Okay, sit right on this stool, face your classmates, and you have a pretty flat head, right? Right. So anyway, we're going to do a demonstration that involves surface tension of water. Now you've probably all seen the old demonstration where they pull a tablecloth out from underneath the older dishes and stuff like that. Well, this is kind of the same thing. I haven't really done this before. Well, I kind of practiced, but did you bring a change of clothes by the chance? Oh, that's too bad. Okay, well we'll try to get it right, but you never know what's going to happen. This is physics after all. Okay, so water tension is that thing. If you put water in a glass, you can see the little meniscus on the side where it climbs up. Well, that's the tension with the forces between the molecules. So if I take a flat piece of cardboard, or in this case a piece of plastic, and I turn it over, the water doesn't leak out. There's a little gap between that plastic and the cup, but it's not enough for the water to leak out. So, now she has actually very good hair for this because it's very fine. And you can actually do this with hair because the gap between hair is really close together. So this takes a little bit of technique. Don't try this at home. So what I'm going to do, this is where that tablecloth analogy comes in. Now, I just realized something. Like I said, I didn't really practice this. I hadn't really thought about how to get the cup off.
Just lift it up.
Do you feel any water on your head?
No.
Well, that's good. It's working. All the little molecular forces between the hairs, there's no water getting through.
Oh.
Pretty impressive, huh? Yeah. Okay.
Is there no water on the head? Wait, there was no water on the cup.
Oh, wait a minute. You saw me.
I thought there was water in the cup.
You saw me pour water in the cup, didn't you? Who saw me pour water in the cup? Oh, good. Everyone's watching.
Whoa.
What's in there now? Okay, you can go back. Thank you. So a lot of that, some of that was true, what I said. It's mostly true, wasn't it?
That's not water.
No, water's still in there. I'll pass this around. This is actually one of the most important chemicals ever invented, at least as far as parents are concerned, because this is the stuff they put in diapers. This is sodium polyacrylate. It can absorb hundreds of times its own weight in water. So when I poured water in there was a little bit of white powder in the bottom, very tiny amount. So as soon as I poured it in, it solidified. Okay? So this is just a fun example to get you guys thinking of a property of a material that's kind of nifty. Okay? The thing I said about surface tension is true, it just doesn't work like that. She would have gotten really wet. Okay, I'll pass this around. Do not eat it or take it out of the cup. Okay.
Don't eat it, guys.
Luke's going to take care of this from here on out. And I'm going to eat a bath.
So we are going to talk a little bit more about other types of materials. And one of the things that, anybody here plays sports? Some of you like to play sports. So a lot of sports are based on, you've got a ball, maybe a basketball or a tennis ball, and they bounce. Except when they don't. So we can have a rubber ball, and that rubber ball can bounce or not. In this case, I've actually got two rubber balls, and they look pretty similar. They've got about the same density, the same mass, both made out of rubber. But they behave differently. The material property of these are different. One of these has a high coefficient of restitution, which means it bounces. And the other one, not so much. And the difference between these two balls, both rubber, is a process called vulcanization. It's a heat treatment. You studied your Greek mythology, Vulcan being volcanoes, fire god. So that heat treatment can actually change the molecular structure of how the molecules inside there bind together and either make them bouncy or not. So we often like to have some bounce in our sporting equipment. It's no fun to try and dribble a flat ball, but we can also have, sometimes the bounce goes away. So I've got a tennis ball here. It's got a little tiny bit of a hole in it, and it doesn't bounce particularly well. But sometimes you can combine materials. You can add two things together and get different properties as a result. So I'm going to try and use the bounce of the basketball with the tennis ball. So the tennis ball by itself doesn't bounce more than a foot. The basketball bounces maybe 2 feet. How high do we think we can bounce the tennis ball if we bounce it on top of the basketball?
3 feet.
3 feet, 2 feet plus 1 feet?
Yeah.
All right, shall I give it a shot? So 3 feet should come up just above the top of the tables. Ready?
It smells so weird. Oh, what? It was sick.
You said 3 feet.
That was like 3 feet times like 10.
No.
Not that much.
These ceilings are
In distance, it went about 30. It went about 30 feet away.
We're 30 feet away.
Let's try that. Watch that again. So it's the same. Unlike the last time, I didn't, swap the ball. It's the same dead tennis ball. You can do this at home with a tennis ball and a basketball, or a super ball and a basketball if you've got a really high ceiling.
It's a super ball.
Somebody say, what's a Super Bowl?
That was him.
Yeah, that was me.
Oh, I think
A rubber bouncy ball.
we're a little dated, I guess.
We are.
When we were young, there was one kind of bouncy
It's like-
ball. That was a Super
It's like
Bowl.
a pink thing, right?
Well,
Yeah.
it should like a basketball.
Yeah.
That's like.
So the basketball compresses just a little tiny bit when it bounces off the floor. So it's squeezing down, and the tennis ball sits on top of it, and the tennis ball squeezes just a little bit. But as the basketball is starting to bounce back, it gives a little kick to the tennis ball, which is sitting right on top. So the basketball has been squeezed, and then as the tennis ball is saying, I'm going to start bouncing, the basketball also pushes back. And so those two things together end up giving the tennis ball a lot more. It's stealing some of the bounce of the basketball. And the more mass here means that it has plenty of energy to give up, to kind of kick that a little bit higher. So we're going to talk about some other properties of materials. We've got 2 plates. Which one feels warmer to you? This one feels warmer, all right? Not anything. Which one feels warmer to you? All right, agreed. This one feels warmer. Which one feels warmer to you? This one. So everybody that I've asked says this one feels warmer than this one. I'm going to put 2 ice cubes. Warmer, colder. Which one do you think will melt faster? Which ice cube? On the
Older one.
the warmer plate or the colder plate? So if you think the warmer plate will melt the ice cube faster, raise your hand. If you think the colder plate will melt the ice cube faster, and if you think we've done enough that you don't trust any of us,
Yes.
now you have the healthy attitude towards science. Do the investigation. Science is intrinsically an experimental endeavor. Without the experiment, without the observation, where are we going to be? So we have one that felt warmer, one that felt colder, and we've got them both sitting, these ice cubes sitting there, and we're checking to see whether or not they're melting. It's a little more exciting than watching paint dry. But we're going to leave that there and talk just briefly about some other things, and we'll check back in as that happens. All right, I need another volunteer.
I
You got me? All right, come on up. Josh. All right. Grab that hook and just pick that right up for me.
Oh, it's like a drum pad. Yeah, it is. It'll come on.
All right, stand over on this side so they can see.
Didn't have breakfast
That's
this
seriously
morning.
what.
Can you pick that up for me?
Come on, Josh. Yes.
Is that a little trickier than you expected? Kinda. All right, give it a pull. And while you're holding that, use your other hand and just gently lift up one corner. All right, do it over on this table so they can see too. So right
It's
here,
exactly like a drum pad.
try and pull that up.
What?
So what do you think's going on? Why is he having a hard time? It's not heavy once he's got it up.
Bigger on the wall. It's like suction.
It's like suction. It's more than just like suction. It is suction. Thank you very much. So, it's not that... So, what does it mean to be suction in this case? Why is it hard unless we break that seal? What's going on there?
Like vacuum sealed, so like it's like
It is vacuum sealed.
yeah, like the air on the sides can't get in, so it's kind of build up.
So I'm trying to pull against air. There's over 14 pounds of air pressure pushing on every square inch of you. So not that big. 14 pounds
I got the
on
ice.
that, pushing on you, but it's pushing on every side. All right, brief hiatus. This was the warmer plate. This was the colder plate. Where's my ice cube? How are we doing?
It's non-existent. He's a little bit moist.
So that was my cold plate, and this is the warm plate, which is left me an ice cube. Normally, heat is what we use to melt ice. Thanks. And this one felt colder, but was room temperature. Like they'd both been sitting on the table since before you guys got here. So they were both at room temperature. So was one of them actually colder or one of them actually warmer? If they were both room temperature?
It might have been a chemical reaction, like the oils on your skin might have
Oh, interesting. We might have done something like that. But these are different materials with different properties. This one's metal. It's aluminum. Metal is a good conductor of... Good question. Same ice in this case. We pulled a lot of fast ones. I would understand why you come across the same.
They both came out of my refrigerator at home.
Both ice cubes. This one is metal and conducts heat reasonably well. It allows heat to flow reasonably well. This one is foam. It's actually an insulator. It's like your thermos or your coat. It blocks the flow of heat. So when you, warmer than room temperature, touch something at room temperature, heat is flowing out of you. That happens all the time. You're constantly giving off heat. But if you touch something that's an insulator, you don't feel much heat flow out of you. If you touch something that conducts heat well, it's like licking a flagpole out on the playground. Something hopefully none of you have done. But you can feel that heat go out of you quickly. Everyone can try this really quick. Put one hand on the table and one hand on the metal bar near your table. They're both at room temperature. Which one feels colder? So this is a nice a nice party trick for physicists, but the same thing actually applies on the space shuttle. And other space reentry vehicles. They make insulating tiles. So this is an actual space shuttle tile. We got it when the space shuttle program closed down. It only weighs about 400 grams. It's 94% air, 94% empty space. But it's a great insulator to prevent those incredible heats that build up inside. We're going to do one more air pressure demo, I believe. Oh, two more. I forgot. Fire. Should I forget fire? No. Shouldn't forget the fire.
What are you going to do? Do it right here.
Yeah.
I missed you on camera once.
I've got a cylinder with a big red button. What should we do with a big red button? We should press the button. So I can press the button and I can compress the cylinder, but not much happens. It doesn't go all the way in. It looks kind of like a syringe going in. And you'll notice I can't press it all the way down to the bottom. There's air inside there, and I'm squeezing the air. The air gets squeezed by the compression. So what would happen if we put something combustible, like a match head, inside air that we were squeezing? What happens when you compress something? So one match head inside an otherwise empty container, and we know that the syringe head doesn't make it all the way down. Can we get the lights?
Yep. You're going to do it right there. Okay, make sure everybody can see the base before I turn off the light.
Alright, I'm going to compress it, and I'm going to compress it pretty fast.
Oh, yeah, that's cool.
So, what did you observe?
It exploded or it combusted.
Now, I didn't strike the match. We saw that the syringe didn't make it all the way down to the bottom, but the match head did combust. The temperature change of just squeezing the air molecules momentarily warmed up that little pocket of air enough to actually spontaneously ignite a match. You can do the other thing going the other way. If you allow a gas to expand, it will actually cool off. That's the basis of the compressor in most of your refrigerators or freezers, is allowing a gas to expand.
We have just been using some density compression
Oh.
of gas particles. This is perfect. So can I ask a question?
Please.
So we talked about developing a particle model of gases, and if we compress them, those gas particles are going to get closer together. And so, how is it heating up the match? Is it the friction of the particles rubbing against the match, or is it just that they're bouncing around more? Like, what is causing the match to combust?
A great deep question. There's temperature is a measure of the average energy of the gas particles. And so the temperature of the gas particles goes up when I compress it. And it's not necessarily a frictional effect, but I have more bounces on. So with friction, we usually think of something moving past something. Like if you rub your hands back and forth, that friction is kind of a macroscopic phenomenon of warming things up. And it's not that one air molecule is going up to the match head and rubbing on the match head. Every single air molecule is going to bounce off because it's a gas.
Yeah.
But that bouncing at a higher rate, and as I'm pushing down on the syringe, I'm doing work, and I'm raising the temperature of the gas. And so if you took a book of matches and put them in an oven and ran them high enough, you could spontaneously ignite your matches just by virtue of being in a hot area. So, anyone read Fahrenheit 451? The temperature that paper spontaneously burns at? You might get to it. Should burn. But everything will have a temperature where there's enough thermal energy around that it'll just start burning in the presence of oxygen. I did, yeah. All right. Oh, we're going to leave this. We're going to do the. We got.
Oh, we're doing acoustics anyway.
So I want to talk about air moving a little bit. We're going to move away from fire, and we're instead going to talk about sound waves. So I've got a speaker here. It's a little bigger than one of your earbuds. Please don't try and put this right in your ear. But we're going to create a sound wave inside this tube. Some of it will leak out and you might hear it. And sound waves, like ocean waves or waves on a string, they have dimensions. They have amplitude, they have length, they have a wavelength. And if we hit a resonance, if we hit a spot where the sound waves exactly fit in this tube, they can start building up an amplitude.
Okay, so what I have here is a function generator, which just is generating the sine wave of the tone you hear, and I can change. Whoops, sorry, hold on. So I can change the frequency, and I'm going to shift that over so I change it to a much finer frequency. Hold on.
Sounds like Ace's music.
I guess taking on another spell.
That's what I thought.
Yeah, he's not here, right? He's in the other person.
Probably just as well then.
Let him know you said that.
Okay, and the other box I have is a power amplifier, so I can change the volume. And what I'm going to do is ramp up the volume. You can plug your ears if any of these tones hurt you, or you find uncomfortable. And actually, we should close the door.
So what do you notice starting to happen?
Oh, they're vibrating. You see them moving to the other end.
Now I'm going to shift the frequency.
Almost like sucking them. They make them fly.
Now I'm going to turn the volume up. Change the frequency a little bit. Okay.
So sound waves are compression waves in the air. It's high pressure and low pressure. It's like when you're all waiting in line to get on the bus, and somebody at the back of the line trips and pushes the person in front of them. And then those two people are really close, and so they fall away and they push the next person. That push makes its way through the line. The same thing can happen in molecules bouncing around in the air. So you get regions of compression, rarefication, where it's low pressure. And that low pressure can actually pick things up. So those very light objects in that low pressure on the other side of them can lift them up. You want to do it one more time? And so we're using that low pressure to actually pick things up. And you'll notice they're regularly spaced. That's the wavelength. It's actually half the wavelength in this case. But that spacing is indicative of the sound wave. And if we used a different frequency, we would get a different spacing. But we need it to fit exactly in the tube, which is a little tricky. It's also hard to see by eye. Is it? There. Here we go.
Oh no.
See, you all have much better electronics. This is what video games sounded like back when I was a kid. So the spacing there is different than what we had last time.
That was double the frequency of the first one. 55.
So we're going to do another sound pressure, air pressure demonstration. And in this case, we're going to go to extreme. we have regular atmospheric pressure out here, and we have a tube, a long tube with a ping pong ball at one end. And right now, there's air inside the tube and outside the tube. We're going to use a vacuum pump to take the air out of inside the tube. Now right now there's a thin piece of plastic, a little plastic tape on both ends of the tube. Ready? So it's sealed. We're going to take the air out. And so the ball will originally move this way, but then eventually we're going to let the air back in. Specifically, we're going to let the air in on this side. What's going to happen if there's a bunch of air over here, and you've got a particle model of air, and there's no air inside here, where does the air want to go? And what's going to happen to a ball in between the air? It's going to get pushed. And so it's going to accelerate over the entire length of this tube until it runs into a thin piece of plastic on the other side. How fast do you think that ball might be going? 10 miles an hour? 30 miles an hour?
60 miles an hour.
60 miles an hour? 190? Our best measurements, and it's a little hard to measure, our best estimate is about 400 miles an hour from all the end of this.
We actually measured it.
We did measure it.
I think
So we're going to send that ball, and it won't get stopped by a piece of tape. Probably won't get stopped by a ping pong ball. We haven't put a dent in the cabinet yet. But you probably want to close your ears for this one.
it's going to be really loud. Okay, you want to watch the end? Okay, ready? Here we go.
That's so cool.
Wait, is it inside?
What?
Time travel.
So we'll
So
start
watch
this
watch the chair, Magnus. You're welcome to look at it.
No way.
Look, don't pull it open.
I forgot the cobalt.
All right. So that's air pressure. Your teacher can keep that for the momentum of your
Thank you. Awesome.
So we're going to shift a little bit into electricity and magnetism now. So I have a magnet here, and magnets stick to metal. Do they stick to all types of metal? So I have an aluminum block here, and the aluminum doesn't stick. What metals stick to magnets? Iron, nickel. Anyone else remember another one? Magnetite isn't a metal. It is magnetic. It's not a metal. It's a compound of a bunch of different materials. So this is actually a nickel rod, iron, nickel, cobalt, which you probably don't interact with much on a regular basis. Anyone know what this is? You were all really familiar with that.
Yeah.
And kids.
I use that all the time.
There we go. Right? That's a lot. So, what does a blowtorch do?
It blows gas out and
It ignites it. And what can I use that gas to do? Heat stuff. So I've got a chunk of nickel here that's currently feeling the magnetic field of the magnet and being pulled towards it. But if I heat that nickel up, I'm causing a lot of vibration. The thermal energy of that nickel is getting higher. The temperature is going up. And magnetism at a molecular level relies on the alignment of the electrons with the magnetic field. If they have too much energy, you're bouncing around, you can't stay aligned with something, so we expect at some temperature the magnetism might be affected. I didn't touch it. All I did was heat it up. All I did was heat the metal up, and that extra thermal energy, that molecular vibration down at the low level, at the molecular level, prevented the electrons from lining up with the magnetic field. There's the evidence that I've heated up. Here it sizzles as it goes under water. If we cool it down again, we take away that thermal energy, and the magnetism comes back. So that temperature is called the Curie temperature. Anyone heard of Curie? Madame Curie? Or a few people who win the Nobel Prize in both physics and chemistry. So she did some studying of magnetism. But magnetism is a property of material, how the electrons inside that material actually end up lining up. But if it has to do with the electrons, then we expect that it might actually be affected by electrical current. Battery, coil of wire. This is a compass. It's a compass that I can turn in different directions. I'd love to talk about the dip angle, but we won't get into that right now. Look it up on Wikipedia. But it's the dip angle. So I'm going to have that coil on the end of a compass and drive a current through that coil. One more. And I made a magnet. Some of you might have done this before. What's the term that we call for a magnet that we create with electrical current?
Electromagnet.
An electromagnet. Alright, I've got a bigger coil. And what do you notice that I have inside the coil?
Copper wire.
Copper wire is the coil, but there's also an iron nail inside. And as you mentioned earlier, iron can be magnetic. Now, it's not currently magnetic, but I'm going to run, what do you think? 5? 10?
16.
15 amps?
6.
So we're going to run 15 amps. You might notice it start to affect the compass. So I've created a magnet. If I get rid of the current, some of the magnet's still there. I've magnetized the iron. So I've magnetized it even when I haven't. Even when I'm not running any electricity through, I've successfully magnetized the iron. If I run an alternating current, first one direction and the other, then the magnetic field in the iron gets built up and then switches to the other way. So let's try running an AC field in. Even that AC, that alternating current, can create a magnet. But now when I turn it off, the magnet gets a little weaker. As I drop that back down, the current goes away because that, with the DC current, everything was pushing it to a line in one direction, and then I went the other way with an AC current switching back and forth. It doesn't build up that magnetism in the same way. All right. So currents can create magnetic fields. Magnetic fields can create currents. This one. So I've got a light, I've got another coil, this one's even bigger. I've got a big magnet. I'm going to drive, could you get the lights, kid? I'm going to put the magnet into my coil and watch what happens on the light. All right, so you can't see what I'm doing, but hopefully you can see the light coming on. Go ahead and turn on the lights. So when the magnet goes into the coil, one light comes on. When the magnet goes out of the coil, the other light comes on. This is the principle of how generators work. We're going to make it a little more visible by using, instead of light bulbs, we'll actually have a voltmeter, so we'll measure the electrical push, and this is what drives the current that turns on the light. So when the magnet goes in, the needle goes one way. It's not enough just to leave the magnet there. The magnetic field by itself doesn't do it. It's the motion. That changing magnetic field gives me an electrical push that can create a current. So when it goes in, it comes this way. When it goes out, it goes that way. What do you think will happen if I pull the magnet all the way through? Will the needle go back this way or over that way?
That way.
One vote for that way?
Yes. I vote.
All right, give it a shot. Yep. The change in the magnetic field going through the loop is what drives that current. So now we know that magnetic fields can be created by currents, and currents can create magnetic fields. So if I have a strong magnet and a good conductor of electricity, aluminum, not intrinsically magnetic, this strong magnet can create currents, which can create magnetic fields. What do we expect to have happen? Will it get stuck in there because there's a magnet? But if it gets stuck, it's not moving anymore, and it was the motion of the magnet. So let's just try and drop it through. Now, if it's just aluminum, if it's not a magnet, it doesn't create any magnetic field. It doesn't create any current, and it just rolls right through. Now the aluminum is actually just a little bit bigger than my magnet, so we know that the magnet is not getting stuck. The magnet is creating currents in this, which create a magnetic field which push back against it. It can't quite stop it, because if it stops it, there's no magnetic change, so there's no current, so there's no field to push back. So it's a self-limiting effect.
Wait,
All right.
put the aluminum on top of the magnet.
Whoa.
The aluminum on top of the magnet. What do we think is going to happen?
It's going to drop faster, but not that fast.
Just because it's so here.
So there's a little more mass that it's pushing back. It was faster, but not as fast as if I put the aluminum on the bottom side. It would just make it through. All right. Actually, let me keep that magnet. I have another coil. Oh, right. Dave's got one too. Yeah.
Okay. So this is kind of the same thing over there, except we don't have a hollow tube. We just got a big chunk of copper. It's a real thick chunk of copper. And slightly different shaped magnet. Okay. I'm going to take the magnet and I'm going to drop it, say from this height onto the copper plate. What's going to happen?
Oh, it's gonna float.
Excuse me?
Is it gonna float?
It's going to float? I don't know. I'm asking you.
It's gonna like float.
Maybe it's going to float. Even the guy who said float doesn't believe it. Alright. How many it's going to hit the copper plate? It's going to, bang off the copper plate.
It's going to bounce around.
Any other options? Alright, well, let's do the little experiment. Everybody watching? Okay, everybody heard it hit?
You're right.
Let's try that again. Okay? So the same effect that caused that magnet to drop slowly is happening in this copper plate. The flowing magnetic field is generating current in the plate that produces its own magnetic field.
Yeah,
but it's in the other direction, so it pushes against it.
Is there like a lighter magnitude fluid?
No, it will never float.
So
It will always gently come down because it's related on the change of the magnetic field with time.
now, related to that is the copper is dissipating energy. As the current flows around in the copper, energy is dissipated, that magnetic field dies. If we had a perfect conductor, one might say a superconductor, then the current wouldn't dissipate any energy. And with a superconductor, you can't actually permanently float a magnet.
Oh my god, that's so satisfying.
I like that best.
Unfortunately, material scientists have not managed to create a superconductor at room temperature. Our best superconductor is still even colder than Vermont to function. Liquid
That's pretty
nitrogen
cold.
temperatures, that range. With a perfect conductor that didn't dissipate any energy, you can't actually permanently float a magnet. You could actually get levitation. We can do some amount of levitation without them, but we have to continually supply energy to the system. All right. Coil connected to our power supply here at the table. So AC current, alternating current, goes one way and the other. We know that that coil can create a magnetic field. And so if I run that, it reacts with the magnet. But because the field is shifting one way and then the other, the magnet gets pulled in and pushed away, and so it just kind of rattles around. It can't find a happy medium. Did it?
Yeah, what's that?
We have more choice.
Yep, you blew a breaker.
Every now and then we break something.
So let's try it.
Yeah, get your big magnet out of the way. All right. So, electric currents can create magnets. Magnets can create currents. Currents can be used to light up light bulbs. Dave, I broke another one.
Oh, no, poke it out. That's right.
We pull fast ones on each other too. So that coil is not touching, there's no contact there, but when I drive a current through, I can light up the light bulb. But we talked about how currents create magnetic fields and iron and other ferrous materials can strengthen a magnetic field. So now, if I have an iron core going through my coil, and I energize the coil with a current, what do we expect to have happen to the light bulb? Brighter? Who thinks brighter? Who thinks not going to work? Because it's me pressing the button. Fair enough. All right, let's give it a shot. A little brighter? All right, let's try the inverse of our cow magnet. Now I've got a magnetic field. It's a changing magnetic field. And I've got a copper, an aluminum ring. Is aluminum magnetic? No. So, should the aluminum react in the presence of a magnetic field? So I shouldn't get any effect if I turn on the magnetic field now? Remember, this is AC current. It's a changing magnetic field. That changing magnetic field can create electrical current, which creates the magnetic field, goes the other direction. Also an aluminum ring. This one's got a cut in it. So whereas this one, the current can go all the way around the ring, with this one, the current can't make it all the way around the ring. So the current has just little tiny loops in the edges it can go. Do we expect more effect or less effect? Now I can't make a big circuit. Who thinks less effect?
Less.
Who thinks more effect? Science is an experimental endeavor. Let's try the experiment. Little effect, not much. It twitches like you trying to get out of bed in the morning. But it doesn't jump. What can we do to get a better jump off the ring? Put
Oh, yo, try that. Can we see what happens?
this and then this.
Can we put the aluminum thing on the bottom and then put the oil on top of it?
So the coil is a lot heavier, so it would react, but it's not enough to lift the coil. So we're going to strengthen the magnetic field. We saw with the light bulb that we strengthened that magnetic field. But now we're going to run that through. Same one that jumped about this high before. Ready? Set.
Maybe with the light.
So by strengthening the magnetic field, we can make that ring jump a little higher. One small detail. It's not a solid core. This is a transformer core. Where's that phrase? So the question was, if it was fully solid, would it go even higher? Great question. There's a couple of different effects that compete. If it was solid iron, that would strengthen the magnet even more. But if it had that solid iron, the current would actually set up in the iron to oppose the magnetic field. Whereas by breaking it, by having lots of little rods, we prevent a big current from setting up. And so we actually deliberately use strands. We take a small hit on the magnetism, but we don't get an opposing magnetic field from the induction. Great question. All right. Oh God, that thing. No, there's no safe place when he pulls that out. So this is the culmination of everything that we've been talking about in the electricity and magnetism part. He's got a coil here. He's energizing a bank of capacitors. Now batteries will give some current at some voltage for a long time. Capacitors store up electrical energy and then can discharge it, in this case, very, very quickly. So he's going to charge it up to, I don't know, 10,000. Really? 10,000? So he's going to put 10,000 volts. I'm dealing with 120 volts from our wall outlet. So he's got 10,000 volts, and he's going to dump that into a coil of wire and create a magnetic field really quickly. Remember, changing magnetic fields create currents. Currents create magnetic fields in opposition to what's been created previously. What? There's too many lights. Yeah. So what do we expect is going to happen to the can? It's going to, the middle's going to get crushed, the outsides are going to get... So, why am I standing? I'm going to go stand behind you.
Okay, so you're correct. These were cans that were put in this machine at different levels of voltage. We're charging up with the same one here, and hopefully we'll get that same result. So as we pointed out, we're charging these capacitors, which store energy, and we're going to dump that energy through a coil of wire that's effectively around that soda can. And that soda can is free to move in there. And I'm slowly charging up the capacitors with the power supply, without so much voltage in there. These lights are more for your amusement. The top one lights are about 10,000 volts right now.
I think we can meter back here around 8,000. And slowly ramp it off the voltage of our power supply. So when I cut the string back here with the weight on it, there's a switch that's going to drop. That's going to disconnect the power supply and at the same time short the capacitor to that coil. It's just about the same size as the can. That huge magnetic field that's produced by pretty much 20,000 amperes very instantaneously running through that coil. It's going to produce a very, very high field. It's going to produce a very high current in the can. The can is actually going to be hot enough to melt a little bit. And it's going to feel a force inward, which you really couldn't see with the jumper today. But it's going to feel a force outward on both ends, which is the same force that the ring felt when it jumped. So this is essentially just like the jumping ring, with two of them end horizontal. Okay, so you get a crushing, pinching force, and then a force outward on both. And again, this is going to be very, very loud.
I'll reiterate, this part's going to be loud.
It's going to be louder than the pink. I'll tell you when I'm going to cut the string, but feel free to keep your finger warm. Okay, we're about 9,500 volts. Dangerously close. All right, here we are, 10,000 fingers in. Luke will pass those around. Feel free to take them with you. You should be able to feel it's still warm. Those of you who get to it in time. Okay? Yeah, I told you. Okay.